Sorry. I love it. Can I do it on purpose? I didn't realize. Oh, honestly, I'm gonna start doing it. I should go up here. Yes, this one has issues. Huh? No, this one is have reasons for a lot of people. Issues? Something like that. It's really. Pretty much. Like you try to You got this. Like I go to
bread and butter. I'm telling you now. Start there's a bunch of relationships.
And grab some water.
So like, I'm trying to turn left. So I'm going up around and turning right. Someone's turning. They're going so slow. They stop and reverse. What's going on?
Oh, if you want to remove the refinement, just right click the refinement object and just say remove. So when you're in ANSYS Mechanical under mesh, you see that kind of that entry in the project outline that says refinement. Just right click it, and then there will be something in the menu called remove. So that's how you.
Quick question. So on the homework set that you at least it says that to provide like the gradient or like the changes of like the whole like being stretched out, so like the color parts. So what do you want us to do there? Like get like a snapshot of like,
Yeah, just a screenshot.
oh, just a
Yeah,
screenshot.
so for the activities, and we'll talk about it today. I don't want you to submit any answers files. I want you to summarize everything into a PDF report and submit.
Oh, okay. All right.
You get it? What's up? Oh, okay, so you can do that, and so there is a petition for it. So a few things have to happen. So first of all, you have to, because normally for an undergrad, you can take 4 technical electives. And so you can't double count. And so this would have to be the 5th technical elective, or you have to have 5 and 4 in order for this. And then you would also have to do, because like for grad students in the corner of the class, you have to do an extra assignment. You have to do that.
Never mind.
Yeah. Yeah, so for all the questions that I asked you, a question of in the PDF, I do want you to write those down and submit those. Yeah. We'll talk about it today. And so basically, for the activities, I don't want you to submit any of the answers files. I just want you to summarize it all into a report. So in that report, you would have the answers to all the questions, as well as screenshots that show your answers to those. Yeah.
I was gonna download it. This is on my own desktop. There were like, when I went on Answers website, there were like 40 different things to download. I don't know which one.
Yeah, so the only one you need is just answer student. So it should be the first one on the list. So usually what I do is search. Student. The one you want is this one right here.
Okay.
Yeah, so that's gonna have the same interface. So I think some of these are like, this is like has a different interface. And so it's used for more education, but I personally don't like it. And some of these are kind of for more specialized cases. The most general one is this one. Yeah. All right, it's 5:30, so let's go ahead and get started. All right, good evening, everyone. How's everyone doing today? Everyone enjoy Antis last Thursday?
Yeah.
Yeah, good, good. All right. Okay. I've gotten a lot of questions on, how you should submit the ANSYS activity. All right, guys, come on, let's get started today. Okay, so I've gotten a lot of questions on, how the ANSYS activity should be submitted. And so I don't want any of your ANSYS files, because there are, almost 50 of you, and I can't open up ANSYS 50 times. So, when you're submitting your work for the ANSYS activities, what I want you to do is to just write out a report. And so if you read through the PDF, there will be times in the PDF where I ask you to, run the simulation and then produce these screenshots. And so if you guys can run the simulations, produce the screenshots, and then put them in the PDF, into one PDF, and then that's what I want to see. And what you'll see throughout the activities too is that I ask you questions as well in terms of things like, what's the maximum deformation that you find? What's the maximum stress? And so, the answers to those questions can also go into your report as well. Okay. And so, for all the ANSYS activities, we did one last week, and we're going to do, several more throughout the semester. I just want the PDF of your, of your report. Okay. So no ANSYS files, just one PDF, which has all your screenshots, all the answers to questions, and then submit that to Canvas. Okay. Another question I've been asked is in terms of the version. And so we have a little bit of a mix up right now, because I know the version of ANSYS that we have here on these computers is 2021. But if you downloaded the student version of ANSYS from the website to work at home, the default that they give you is 2022. And so what's going to happen is that if you start working on the project in class and then you take it home, it's going to kind of upscale your files to 2022. But then if you try to work on them back here, there's going to be a version mismatch. And so I need to look into it a bit more. What I'm hoping for is that you can download you can find an archive somewhere to download 2021. But let me look into that this evening, and I'll get you guys some information on how to get the right version in between. So, so we don't have this version mismatch between the home version and what you have here. Okay. Okay, and so with that said, today is just going to be just a regular lecture day. And so the schedule for this class is that, we're going to do an ANSYS activity approximately every other week. And so we did one last Thursday. And so the next time that we do an ANSYS activity is not this Thursday, but the following Thursday. And so all the in-between classes are just going to be straight up lectures in terms of the theory behind FEA, in terms of, what are some techniques that you can learn as well. Okay. And typically the way this is going to go is that, for the 3 lectures that lead up to an activity, we're going to be talking about certain features, certain techniques, things like meshing, things like boundary conditions, things like material properties, and then we're going to apply that in the activity that kind of follows that. Okay. Okay, and so that's all my announcements. And so remember, the activity is due by this Friday at 11:59. And so make sure you're kind of doing that and turn that in time. Okay. All right, and so any questions I can answer before we get started for today? You'll see me peek around here a lot because this computer screen, I don't know how to lower it, because if I lower it, it just pops right back up. And so, every now and then I'm gonna peek around to see if there's any questions on there. So that's kind of why I do that. Okay, and so the lecture for today is gonna be, I call it the theory behind FEA, which, if I were talking to any of my colleagues and I said I summed up the theory of FEA in one lecture, they'll probably just slap me across the face. And so, this is a very, very, very much a very brief overview. And so if you're interested in learning more about this, we have other classes in FEA, mostly at the 500 level, that go much deeper than this. But I did want to give you guys a perspective of, what FEA is. It's more than just ANSYS. ANSYS is just an application that uses FEA. And so FEA as a theory goes much deeper than that. And I wanted to give you a sense of that today so that, so that you kind of just have an idea going forward. And it also helps us to understand parts of using ANSYS as well. Okay. So I guess, very basically, I say FEA a lot just because it's a lot to say finite elements. But when I say FEA, what I specifically mean is finite element analysis. Okay. And so the thing about FEA that I think a lot of people don't realize is that it's actually not strictly a computer program. Okay. And in fact, at its core, FEA has actually nothing to do with computers and really nothing to do with engineering at all. Right. And in fact, when finite elements was kind of first proposed or kind of first discovered as a theory, it wasn't very popular at all. It took a very long time for finite elements to actually become practical and for people to actually start using it. Okay, and you'll find out why in just a second. And so finite elements, what it basically is that it's a way to transform one type of math problem into a different type of math problem. Okay. In particular, finite elements allows us to take a differential equation and transform it into a system of algebraic equations. Okay. And I'm going to put a qualifier here. So, it's not just any system of algebraic equations. It's a very large system of algebraic equations. Okay. So it looks something like this. And so, if you have a differential equation, and so, the one that I like to refer to is the heat equation. Okay. So this is one form of the heat equation. So this is a differential equation. In particular, this is a partial differential equation because we have partial derivatives there. Okay. Right. And through FEA, we can take this differential equation and turn it into a very large system of algebraic equations. Okay. And so when you start to have a very large system of algebraic equations, the way that we typically express it is we put it in matrix form. Right. And so if you remember from your linear algebra class, that if you have say like 10 equations, 10 unknowns, you can put that in a matrix form, and that's a little bit more of an elegant way to produce it or to express it. Okay. Okay, so that in kind of its purest form, that's all that FEA is really, is to take a differential equation and transform it into an algebra problem, basically. Okay. The problem with this is that the size of the algebraic system that this produces is really, really large. Like you're talking about, like even for a very modest, even for the activity you did last week, what I would guess is that the system of equations that form from that is probably on the order of like 5,000 by 5,000, right? So 5,000 equations, 5,000 unknowns. Okay, and so when FEA was kind of first proposed as a theory, on the left-hand side here we have a really freaking difficult math problem. And then we do FEA, we go through all these really complicated procedures, we do shape functions, we do assembly, stuff like that. And what do we get from doing all that work? A really freaking hard math problem. Okay. So it's like, great, you took a math problem, you did all this work on it, which was itself a really hard math problem, and you still end up with a really hard math problem. So it's like, great, thanks, Bob. You didn't really help us out at all. Okay. And so, for a long time, it took FEA a while to kind of get going. But, with the advent of computers, we started to, people started to realize that, computers are really good at certain things, right? They're not good at all things, but they are good at very specific things. Okay. And one specific thing that computers are really good at was algebra. Okay. Right. And so this was huge for FEA because, a differential equation, is really hard to solve, and it's really hard to get a computer to solve a differential equation too. But, if you can get your differential equation into an algebraic form, then the computer is really good at doing this. Okay. And, we're not going to go into this, honestly, because it's a very advanced topic. And so there's a whole area of research called, linear solver algorithms. And so what linear solver algorithms are those are basically sets of computer logic or ways to kind of code into a computer how to solve a system of linear equations. Okay. Okay. And so that goes for even the largest linear systems as well. Okay. Because if you give a human, right, so you tell a human, I have this system of 5,000 equations, 5,000 unknowns, right, and I want you to solve it, that human will probably look at you and be very upset because it takes a very long time to solve that. Or for a computer, and you guys all experienced this last week, right? So for a computer solving a system of 5,000 equations, 5,000 unknowns, it was just a simple click of the button in ANSYS, and within a couple seconds, you already had your solution, right? And so computers are really good at this. And what's interesting is that this is kind of more trivia, but finding good linear solver algorithms is still actually very much a hot topic of research today, because we're still trying to figure out what are the best ways that we can utilize computers to solve a linear system. So if you go to any university with a self-respecting applied math department, there's probably at least one professor there that's researching better linear solver algorithms. That's kind of how intense it is. Okay. But this is great for FEA because now that we have computers, now that we have ways to solve algebra, now FEA starts to really gain some momentum because it can take all these complicated differential equations and put them in a form that we can solve very easily. Okay. And this works out really well for engineering too, because in engineering, a lot of times we're dealing with physical systems, right? We're dealing with structures, we're dealing with thermal systems, fluid systems, right? And it just so happens that all of these physical systems, their behaviors are governed by differential equations. Okay. And so up above there, I have the heat equation. And so I tend to, use more examples for thermal fluids just because that's kind of my background. But even for structural mechanics too, you have differential equations that govern the deformation and stress, in a solid, right? And so you kind of start to see kind of the evolution occur. And so, we have these physical systems. These physical systems are governed by differential equations. And then through FEA, we can take those differential equations, turn it into an algebraic system, and then use the computer to solve that system. Okay, so that's kind of a very, very quick, overview of the history of FEA and its history with engineering. Okay, so I can kind of draw it into a flow chart. Okay, right, and so as a flow chart, we often start with some physical engineering system. From here, we can extract the governing differential equations. Okay. From here, we can use FEA to get a system of algebraic equations. Okay. Then from here, we use computers, and we get a solution to algebra problems. Okay. And from this solution, we can then process it even more to get results of engineering interest. Okay. So those engineering results of interest would be things like deformation field. It would be like the stress field, which are all things that you observed last week in ANSYS. Okay. And so that's kind of the progression of of how where finite elements came from and how it kind of became at this point I would say it's almost married to engineering, right? And so far it seems like a very happy marriage. Okay. All right. Any questions on this so far? Okay. And so what this means is that, we can apply FEA to almost any kind of physical system that's governed by differential equations. Okay. And so if you have a system that's governed by differential equations, then you can apply FEA to it. Right. And so of course we have structural, which is going to be the vast focus of this class. But we also have thermal systems, we have fluid systems. If you looked on ANSYS last week, there's also electromagnetic systems, right? And so there's there's differential equations like that. There's even more kind of specialized topics out there like chemical systems. And so if you're modeling things like combustion reactions, those are modeled by differential equations. There's a lot of aerospace applications, so many things are governed by differential equations. So anything that has a differential equation, you can apply FEA to it. Okay. And so the applications for FEA are very, very vast. Okay. And so that's kind of the history behind FEA. And so let's start talking about, some relevant parts of the theory that I think are important for you as kind of, as you're kind of starting out as learning FEA. Okay. And so the first concept I want to go over is the concept of what's called a boundary value problem. Okay. And so boundary value problem, I shorten it a lot to BVP because it's a little bit longer. Okay. And so in this part, you know, I'm going to focus a lot on, you know, this part right here called the governing differential equations. Okay. Because, you know, we talked about, you know, the governing differential equations, they have to be differential equations, but they have to kind of be set up in a certain way. And I think if you understand, you know, how to set up the differential equations for an FEA, it'll help you, you know, find out, you know, which problems that you're having in engineering actually could be solved in FEA. Okay. Okay. And so let's define it first. And so a boundary value problem, or BVP, is a mathematical expression of the type of problem that finite elements can solve. Okay? Okay. And so what that's saying is that, you know, for every FEA that you do, even in ANSYS, you know, there's an underlying math problem, and that math problem is a BVP. Okay. And so intuitively, you know, I think the easiest way to think of a BVP is that it consists of basically a physical situation with real physics and a physical boundary. Okay. Okay. And so, you know, even though if you're doing FEA, especially in ANSYS, you know, you're not going to be explicitly solving the BVP or even explicitly writing it down most of the time. It is still useful to think about it. And so it is still useful to think that, you know, behind this FEA simulation that I'm running, behind this computer interface, is a math problem. And there's certain features of this math problem that are important to highlight so that, you know, you can start thinking about your engineering problems in terms of the BVP. Okay? So there's three main components to every boundary value problem. And so, you know, if you think of your physical problem in terms of these three components, it helps a lot when you're, you know, setting up the FEA. And some of these components are kind of already baked into the FEA process that we've talked about before, but it's kind of useful to kind of see the mathematical side. Okay. Oh, my microphone changed. Can you guys still hear me on Zoom? Oh, change back. Okay. That's weird. Must be a weird echo in here. Okay. Okay. All right. So the first component that we'll talk about is the domain. All right, so the domain is basically the what and where we're going to be solving our problem. Okay. In some sense, some people call it just this, it's the subject of your simulation. Okay. And so if you think back to our activity last Thursday, our domain was basically our plate with the hole. Okay. So it's the domain is just another word for saying, what's the geometry of our simulation. Okay. And so in the most general sense, and you'll see me draw this figure maybe more than a couple of times this class, but for an arbitrary geometry, and so I call this often the arbitrary potato. Okay. And so and the reason I'm drawing the potato here is just to give you some terminology. Okay. And so you notice I've put a little stamp on my potato here with an omega, right? And this omega here, this refers to the interior of our domain. So I guess continuing on with the potato analogy, the omega would be the soft, white, fleshy stuff inside the potato. And so the other part of the domain that's important to highlight is what I call d omega here. Okay. And d omega here refers to the boundary of the domain. And those are important to analyze because the interior of the domain is going to be subject to certain equations, whereas the boundary is going to be subjected to, first of all, different equations, but the boundary is also going to be where we apply things like boundary conditions, right? And so things like our fixed support, things like our pressure loading, those are almost always applied on the boundaries of the domain. Okay, and so it's important to kind of make the distinction between the two because they have different effects on the solution. All right, and so this part here might be obvious, right? And so whenever you do an FEA, what you're starting with is always the CAD file, right? And so your geometry kind of is always set. But it's still good to think about because whenever you're doing an FEA, you have to always kind of ask yourself, what would make a good domain for the analysis that I'm trying to do. Okay. Yeah. And so I'll give you an example that this is a really good example that I came across maybe 3 years ago. And so for the final project for this class, someone was interested in doing a finite element simulation of some weight equipment, right? And so this particular student goes to the gym a lot, and he was curious about how do the stresses and how does deformation how do those things occur in a lot of his gym equipment. Okay. And so what he found online was this very kind of nice CAD file for, kind of a nice workout station. So there's a bench press. There was like a nice workout station next to it, which held all the weights. Okay. And so I told him like, oh, okay. So this, so what in particular are you trying to analyze? And so what he was interested in is like, if he's doing a bench press, he was interested in seeing how much the bar was going to deflect and what kind of stresses are going to be developing inside the bench press bar. I was like, okay. And so if the bar is the only part of the geometry that you're interested in, you don't really need the CAD file for the bench. You don't really need it for the weight rack. You don't need it for the mirror, right? And so the only part of the domain that you're actually analyzing is just the bar, right? And so let's limit our geometry there because everything else is not really going to be interesting. Yeah.
So for the project, we don't actually have to do the CAD drawings ourselves.
No. Yeah, and so this is not a CAD class, and so if you add the CAD files from somewhere else, then I would recommend that you do that. And so what a lot of people typically do is that they do the project on an aspect of their senior design, and so you might have the CAD files already, and so that's an option. But if you were doing something else, then you can get the CAD files from somewhere else. I mean, granted that you obtain them legally, which is important. I have to say that because some things have happened in the past, but and also that you give credit to whoever did the CAD. And so I want to focus just on the finite element analysis. Is there another question? Okay. Yeah. Copyrights are important, and so we can't just say that this is for education. People still are they're still protecting their IPs as they should. Okay. And so that's part one. Okay. Part two of a boundary value problem are actually the governing equations themselves. Right. And so what the governing equations determine is that this determines basically what kind of physical behavior you're looking to solve for. Okay. And even though I call it governing equations, you don't actually go into ANSYS and type out the differential equation, right? And so that was not the experience that we had last Thursday. And so the form that this usually takes in terms of an ANSYS, in terms of software like ANSYS, is that you choose the type of physics that you want, right? And so if you remember, one of the first things that we did last week in the workbench was that we selected, the type of simulation that we're doing is a static structural simulation, right? And so there are a lot of other options from that list as well. So there was, a static fluid simulation, a static thermal simulation, dynamic simulation, modal simulation, right? And so by choosing the type of physics that you're solving for in ANSYS, you're kind of implicitly choosing what governing equation that you're solving, okay? And again, this might seem like it's obvious, but it's something that you have to think about. And so, you have to think about, what are the relevant physics? What are the relevant things that I'm looking to solve for? Okay? Okay. And so you have to think about, is this going to be a structural problem? Is this going to be a thermal problem? Is this going to be a fluids problem, right? And so these are all important questions that you have to ask. Questions that, at this time you might think are obvious, but, it is really important. Okay. And, once you just kind of start diving deeper into finite elements, there's a lot of variations on this as well, all right? And so even in the realm of something like a structural simulation, there's lots of different structural simulations that you can think to, right? And so you have to think about what kind of material model are you going to use, right? Are you going to have a linear elastic material, or are you going to have some kind of composite material that has nonlinear behavior, right? And so there's lots of questions that you can do, lots of important questions to ask, and these are important to ask because you want to make sure that you get the most accurate results as possible. Okay? All right, and so the third aspect of a boundary value problem are the boundary conditions. Okay? And so boundary conditions basically define all of the external forces or external factors that are acting on your domain. Okay. And so most commonly, your boundary conditions are going to take the form, at least for structures, these are going to be all of your loads and constraints. And so this is really important. I'd say this is probably, the most important part of the boundary value problem to think about, because, you have to think about, how is the outside world, affecting the subject of my simulation, right? And so what are the places where it's going to be fixed? What are the places where it's going to be bearing some load? Right? What are the forces? What are the pressures, right? And so there's a lot of variation that can occur in the boundary conditions, depending on, the physical situation, and it has a huge impact on your results, right? So as an example, for the ANSYS activity we did last week, if you remember, we applied a fixed support on the left side of the plate, and we applied kind of a tensile force on the right. Okay. If we change those boundary conditions, and so let's say that we leave it fixed in the same part, but instead of a tensile force, we apply a shearing force that's pushing upwards, right? That's going to completely change the nature of our solution, right? And so in those cases, our geometry is the same, our governing equations are the same. The only thing that's different are the boundary conditions. Okay. And so it's important to think about, if you have a physical situation, always thinking about how can I turn this into boundary conditions for my simulation. That's a good mindset to get into, because if you start thinking about that, then turning your physical situation into a finite element simulation becomes a lot more smooth of a process. Okay? Okay. Any questions on this? We'll be talking a lot more about boundary conditions, later on in the semester. I think it's after meshing, because boundary conditions are very important, and they're the part that most commonly people kind of mess up. So it's important to really think about them and really do a good job of thinking about them. Okay, and so next thing I want to go over are just some of the types of governing equations that you might see in FEA, or what are some of the more common ones. And by no means is this an exhaustive list, right? So even within ANSYS itself, there are probably, a few dozen types of simulations that you can run. And so we'll go over 3 of them, right? And so that's 3 out of, maybe 50 of them. And so, there's lots of types of simulations out there, but here are kind of, I wanted to list what I think are the most common and what are the most probably useful for, for people kind of just first starting out with FEA, okay? And so remember, FEA can solve any differential equation. As long as it's a differential equation, FEA can solve it. Okay? Sometimes I have a brain fart and I forget how to spell stuff when I. Okay, and so here are kind of a list of the more common ones that you'll find in ANSYS, and as well as other finite element softwares as well. Okay. Okay, and so first one, and the one that we did last Thursday, was a structural mechanics simulation, but in particular, it was a very special kind of structural mechanics called linear elasticity. And so what these equations determine is they determine how elastic objects deform and become stressed from some kind of prescribed mode. Okay. And so this is definitely not my huge area of expertise, although I do run simulations on it. But I'm not as well versed in the theory, and so I had to look this up on Wikipedia. But the equation for linear elasticity is given by the following. And apparently this is an expression of Newton's second law, but it definitely wasn't the Newton's second law that I learned when I was in physics class, right? But you can see some aspects of it, right? And so here we have the second derivative of u with respect to t, where u right here is deformation. Okay. And so if you take the second derivative of deformation with respect to time, that gives you acceleration, okay? And this row right here, this is density. Yeah, it's basically F is equal to ma. It's just the F is quite different. All right, and this F here, this is forces. And so, on the right-hand side there, we have density, which is, almost the same as mass. It's just mass per volume. And so we have density multiplied by acceleration. And so that's like ma. And on the left-hand side here, we have forces basically, right? And so on one hand, we have this F vector, which are all the external forces. Okay. And then this term right here, which is the divergence of sigma, right? This represents the internal stresses of the material. And so basically what this equation is expressing is that for any kind of elastic body underneath undergoing some kind of external loading, there has to be a balance of forces, right? So the internal forces within the material have to balance out the external forces on the material, okay? And all of that equal to mass times acceleration, basically. And so the reason it's called linear elasticity, and so linear is kind of the operative word here, okay? The reason we call it linear elasticity is that the relationship between stress and strain in a linear material is linear. Okay? And so hopefully the following equation is familiar to you. And so a linear elastic material follows the following relationship. And so we have sigma, which is the stress in the material, is equal to E, which is the Young's modulus, multiplied by the strain. Okay. And so that's kind of a simple expression in 1D. Okay. And so this is the very famous Hooke's law. And so the upshot of this, and the reason I'm telling you this is that, you know, this linear relationship is important. So that tells you that the deformations that you observe in the material are directly proportional to the loads that you apply. Deformations and the stresses. And so that means that if you take your simulation under a certain amount of load, okay, so kind of like what we did last Thursday, and then you rerun the simulation, but you reduce those loads by a factor of 2, so you have the loads, then the fact that everything is directly proportional means that the amount of deformation and the amount of stress you see is also going to be cut in half. Okay. And so if I know some of you have actually already finished the activity and turned it in, so thank you for that. But I think a lot of you noticed that there's one part of the activity where I want you to change the loading, right? And so there's one part where I told you to change the loading from 10,000 megapascals, okay? And then I want you to change it to about 9,000. In reality, it was 9,001 megapascals, but we're going from 10,000 to 9,000. Okay, and so this is about a 10% decrease, right? And so we're going from 10,000 to 9,000. So this is spoilers a little bit, but if what you should observe, because we're running a linearly elastic simulation, is that the deformations and the stress that you observe should also decrease by about 10%. And so that's a really important fact to remember about static structural in particular, that it's linearly elastic. Okay? And so if you increase the load by a certain amount, decrease the loading by a certain amount, you should get a linear response from the material. Okay. Okay. Things get more complicated when you add multiple loads, I think, which we'll see in activity 3. But if you have just a single load, this relationship is fairly straightforward. Okay. All right, any questions on this? Okay. All right, one thing I want to highlight here, and I think this is important because I think some of you will start to use it for student projects and for senior design. There are limitations to linear elasticity, right? And so linear elasticity, if you kind of read it up in the textbooks, this type of equation right here, this is only really valid when your deformations are relatively small. Right? So if you have a situation where you start to have larger deformations, you actually need to use different techniques. Question? Exactly, right. Exactly. And so, I think, probably a lot of you are familiar with stress strain curves, right? And so the stress strain curve, for a typical material looks something like this. So there's a linear portion, and then, then you start to get plastic deformation, and failure is like somewhere up here. And so linear elasticity kind of assumes, or let me label these, strain, stress. Okay. And so linear elasticity kind of assumes that you're always kind of in this region right here, which is the linear portion of the stress strain curve. Okay. And so that's even true where, like, if you stretch your material to even greater heights, and so let's say that let's say that you apply a load so big that the stresses are actually kind of up here. Okay. And so what linear elasticity assumes is that this curve is just going to keep continuing upwards like this, right? And so what you're going to get is then a deformation that's much larger than what it actually is. Okay. And you can try this too. And so, if you still have your activity, try increasing the load by a factor of 100 or something, right? And so, try to apply like a gigapascal of pressure, right? And what you'll see is that the deformation will keep increasing, right? And it'll increase to a point where the results are like no longer valid. And so you might get a deformation of like, 200 millimeters when the width of your plate was 200 millimeters. And so, obviously that's not realistic.
So this program is not really good at predicting your models will fail.
It can, it's just you have to account for it. And so, we use kind of the simplest material model so far, and we're going to keep using that for a while just because it's easy. But you can incorporate things like plastic deformation where it'll actually switch over to like, plastic deformation curve. You just have to kind of program it. But, if you're just using static structural just straight out the box, this is kind of what it's going to assume. Yeah. Yeah, so that's kind of why I bring this up. And so, FEA is great, but you have to kind of realize that a lot of the complexities that you kind of understand for how materials behave, how thermal materials behave, you kind of have to explicitly determine or express that in ANSYS. Otherwise, it's going to assume something else. Okay, so knowing the limitations, understanding the equations that kind of go underneath the hood, they're important for what I call kind of responsible use of FEA. All right, any questions on this? All right, and so that's structural, right? And so we're going to be spending most of our time there, but FEA can do a lot more than just structural. And so I think the next easiest one to grasp in FEA is thermal simulations or heat transfer. Right. And so for heat transfer, what these equations determine is how heat or energy kind of propagate through your domain. Okay. And so your heat equation here is basically an expression of conservation of energy. Okay. Right. And what you solve for in thermal simulations is you're basically solving for what the temperature is like at every location inside your domain. Okay. And so the heat equation, I think I mentioned it earlier on, but kind of the more basic form of the heat equation is something that looks like this. So this is strictly just diffusive heat transfer, so no convection, anything like that. So this is pure conduction. And so if you solve for, a thermal, the static thermal simulation within ANSYS, you're basically solving just a pure conduction problem. And so, we're not going to do much with thermal in this class. It's kind of more, for those who are interested in pursuing it. But it's important. It's good to kind of know. Okay. And so if you've taken heat transfer, you probably know what I'm talking about when I say pure conduction. But if you haven't taken heat transfer yet, don't worry about it. We're not really going to do much about it in this class. But that's the equation that we're going to solve. Okay. Or that we would solve if we did thermals. And the third type of equation, the one that I actually have personally worked with the most, is a fluid flow FEA. And so these are your CFD simulations. And so I know some people have written to me already that you're interested in doing CFD. And so CFD is possible with ANSYS. It's just the setup is actually quite different. So this is something that we're also not really going to get much into in this class, but I do have some handouts for you if you are interested. All right, and so what these equations determine is how a fluid will flow inside a domain when it's exposed to certain forces. And so the governing equation for this is, of course, the Navier-Stokes equations. It's 2 years in a row now that I haven't been able to teach fluids, and I'm really sad because I really love fluids. So I say this every year, or every time I teach fluids, I say this, but since I'm not teaching fluids, I'll tell you guys. And so, the Wi-Fi at my home is actually called Navier-Stokes. And my wife keeps thinking that it's some kind of dirty joke, but I'm telling her it's not. It's a famous mathematician that solved a really important problem in fluid mechanics. I've even shown her the equation, but she still thinks it's like something inappropriate, like some kind of weird engineering joke. But it's hard because you show someone this equation, right? And they think they're not really sure what they're looking at. And so she's like, why don't you name our Wi-Fi something normal, like Spectrum Setup 7A or something like that? It's Navier-Stokes. Okay. So that's the Navier-Stokes equations. I have posts. I was like, I'm not gonna name our kid Navier-Stokes. That would be weird. But the Wi-Fi is funny, right? We got a cat recently. I think some of you saw it on the Discord channel. I was kind of petitioning we get a boy cat and we name it Reynolds after Reynolds' number, but then she vetoed that. So we got a girl cat. We named it something normal, and so she's Reynolds. Like Reynolds' number in a.
I know. What's the cat's name?
Oh, her name is Sophie.
Oh.
Yeah. It's cuter than Reynolds, but how can I express my love for fluid mechanics that way? Okay. So as a mechanical engineer, these are probably the ones that you. These are probably going to be the ones that you're going to use the most, in terms of FEA. But there are a lot more. Okay? And like we talked about with the structural ones, there's a lot of variations within these equations too that you have to keep in mind as well. Okay. And so the reason I'm presenting these to you again, is to let you know what these equations are, and most of all, what their limitations are. And so if you are looking at something like failure of materials, you can account for that by applying the appropriate material. Okay, any questions on this? Okay, and so one other thing to keep in mind is that you're not just limited to one type of physics as well. And so a lot of, very practical engineering phenomena, there are multiple kind of physics involved. And so you can actually, in ANSYS, you can actually combine different physics types to solve kind of a very kind of complicated situation. And so whenever you do a situation like this, it's called a multi-physics simulation. And in fact, a lot of the more sophisticated, simulations out there are multi-physics. They don't just stick with just one. So question in the chat: is that a rho or p in the denominator on the right side? Oh, that is a rho. So this is density, and this is pressure. Sorry about that. And so if you want to run a lot of these complicated simulations, you have to, account for all those physics. And so one of my most favorite ones, and I think maybe we'll end it by, I'll show you that. Okay. And so one example of a multi-physics simulation that's really cool to look at is the fluttering of a flag. Okay. And so the situation looks something like this. And so imagine you have a flag and you're looking at it from above. And so you have kind of an aerial view of a flag, right? And so here is the flag post. Okay? Here is the flag itself that's trailing behind it. Okay. Right. And then what you can do is you can, if you've ever seen a flag that's, floating in the wind, you can have a wind that's flowing at it. And if you've ever observed the motion of the flag, you'll see the flag, it doesn't just stay still. It always kind of flutters in the wind just like that, right? And so you're going to have this kind of very interesting motion where, the flag is kind of, fluttering kind of, back and forth like that, right? And so this is a great example of multi-physics. So you have multiple things going on. And so you have, first of all, you have the fluid mechanics of the wind. Was there a question back there? Or is it okay? And so in order to solve this equation, you have to solve the situation, you have to account for the fluid mechanics of the wind. And those fluid mechanics are going to be interesting because as the fluid goes past the flag, it's going to cause little areas where the air is going to go up, it's going to go down. You're going to have little vortices that form, right? But the other thing you have to take into account here is actually the solid mechanics of the flag itself. And so, based on the structural strength of the flag, based on its density, based on its, based on its solid mechanic response, that's going to determine, how it flutters in the wind. Okay. And so you have this interaction between the fluid mechanics of the wind and the solid mechanics of the flag, right? And so in order to properly run a simulation on this, you have to run a simulation that accounts for both fluid flow and solid mechanics. The aerodynamics often doesn't account for the solid mechanics of the object. And so, if you're talking about an airplane wing, airplane wings mostly are kind of, we assume those are kind of stationary in the flow, but here we have a flag that's actually going to be fluttering and responding to it. And so these particular simulations, so these are very common simulations that combine fluids and solids are often kind of paired together in one. And so, there's a whole field of study behind this called fluid structure interaction. And sometimes you'll hear the acronym FSI. Okay? And so FSI stands for fluid structure interaction. And so if you look up on YouTube, you look up FSI simulations, there's a lot of really cool applications. And so one that I've worked on in particular, not the flag fluttering one. The flag fluttering was actually really hard. But one that I've worked on is a lot of my research involves doing simulations of blood flow. And so, if you know anything about the blood vessels in your body, they're not rigid structures, right? And so they're very flexible. And so, the interaction of blood pressure and in terms of, how it pulses your blood vessels, that's a very important FSI problem. And so there's a lot of research going on to determine, what's the best FSI method for pulsating blood vessels, basically. Okay. Any questions on this? Okay. And so the last point that I'll leave you with, and I think we'll probably end a little bit early today. The last point I want to leave you with is that, I know in a class like this where, the main, ANSYS, I know ANSYS is the main attraction in this class. And so, when we do days like this where we just talk about the theory, it can be a little bit slower. And so, I don't have these days just to, just because I'm intentionally keeping you away from ANSYS. I promise you, I'm doing as much ANSYS as we can in this class. But the reason I'm doing this is that, there's a lot more softwares out there other than ANSYS. Okay? So, maybe you guys know this because I know probably a lot of you have used SolidWorks already, but engineering software is not cheap. So, ANSYS, and I can tell you ANSYS because I recently just purchased some myself. In order to just use ANSYS for 1 year, just 1 year, and after that you can't use ANSYS anymore. In order to just use ANSYS, the professional one for 1 year, costs $6,000. Right? And so, after that, ANSYS is like, I take the license back. We have a new version. Get wrecked, and so it's expensive, and so for an engineering company to actually buy ANSYS and use it, it's a significant investment. And what happens a lot is that for a lot of smaller engineering companies out there, they may not be able to afford ANSYS, or even for a larger company, they might have a contract negotiated with a different with a different software. How much does CETA cost? I'm not sure actually, so I have to look. I only know ANSYS just because I personally purchased it for my research. But if you go on the websites, you can't really, they don't really post the prices because that's something you negotiate with the salesman, because the salesman thinks, all right, how much money do you have and how much money can I get from you to pay for the software? So they looked at me, they said, you're a poor professor, you don't have any money, so we'll sell to you for $6,000 per year. I was like, okay, that's fine. And maybe Boeing might be paying more for their ANSYS too. So, there's, I kind of got sidetracked a bit. So, there's other softwares out there to ANSYS. And I don't want you to come out of this class thinking that ANSYS is the only software that you can do, okay? And so whether you're using ANSYS, whether you're using Abacus is another very popular one, I want you to have the confidence that you can go in and you can use the software, right? Because even though the software interfaces might be different and the way that you set things up might be different, FEA is still FEA, right? At the end of the day, it's still going to be the same method underneath the hood. You're still going to be producing a mesh. You're still going to be doing boundary conditions. You're still going to be, importing your geometries and things like that. And so, the reason we have these days like this where we have theory is I want to illustrate to you guys that, there's a lot of kind of theory underneath the hood that you can take to different softwares, okay? And so, what I hope from this class is, yes, I hope everyone comes out of this class as an expert in ANSYS, but I want everyone to have confidence that they can step in and use other softwares as well, okay? All right, any final questions on this before we wrap it up for today? Okay, all right, so that's all I have planned for today. So thank you everyone for coming today. Thanks for tuning in. And I'll see everyone on Thursday.
This other software includes Excel.
Excel is different, but
People do crazy stuff with that thing.
people do crazy stuff in Excel too. Yeah. Excel, I think, is more similar to MATLAB. Actually. So if you have MATLAB, then you
That's
can,
true.
you can do
That's
MATLAB,
expensive
you can do
too.
Excel. MATLAB is only like $100. MATLAB is pretty cheap. Yeah. Yep. MATLAB is one of the cheapest ones out there.
Wow.
The student ones.
Yeah, student one's $100. Oh, okay, yeah. So professional one's probably a lot more.
That's just probably 1,000.
Yeah. It's expensive, which makes sense because you need very specialized professional teams to develop the software, but the audience is very small. So like how many engineers are out there compared to how many people use Facebook or something, right? So
True.
they have to make it expensive so that they can pay their people.
That makes sense, actually, though. I think it's the jack price.
Yeah.
So as far as saving goes for the activity from yesterday, I'm kind of afraid to close it because I don't want to lose any of my work. But I'm not certain once I save it, I'll be able to reopen it and finish the activity.
So what people have told me is that they were able to save it and open it up at home. But if you're running the 2022 version at home, it'll upscale it so you can work
Well,
on it.
it's, I'm doing the work for in class and home on the same laptop. I'm bringing
Okay.
my laptop to class.
Okay.
If I have any issues, just open
Oh,
it.
if you're doing everything on the same laptop, you can just use the normal save. And so what I talked about last time with the archiving, that's if you're transporting between different machines.
But even if I wanted to put it on a flash drive, I could save it just from this normal file structure, archive it, save it directly to the flash drive from there.
Exactly.
Like on the flash.
Well, so if you do it on your laptop, which is likely the 2022 version, you probably won't be able to open it here because these are the 2021 versions. And so you can upscale, but you
These
can't get.
computers to my laptop, but not my laptop.
Exactly.
All right, thank you.
Yeah. Again. Yeah. Yeah. So under the hood means like kind of what we talked about. What's the methods underneath the code? And so the hood, when I define the hood, is stuff you actually click on. So what's happening, what's all the math?
I saw you get 10,000 megapascals.
Yeah.
And on the board, it's
I know
like,
it's about, it should say 10,000.
okay, did the whole thing at 1,000.
That's fine. I have right, and at the end, there's a bunch of like four that's your four. Some of those are, I know, right, for sure. They're not massive.
Yeah, that's what I'm just looking for.
Right, so it would be great. So unfortunately, for this, it was all the funny stuff attached stuff. Yeah, I noticed there was you don't have a schedule for actually next question. For some publication.
Yeah, that was a class.
Yeah, so that one, I think like. Yeah. I'm sorry, I didn't see it. He asked me to read it from a lot of I think what might have happened was that when we made the geometry, remember one of the first things you do is change it to 2D. And so if you don't change it to 2D, it's a 3D simulation that you can only apply pressure on. And so I would double check it. So I would double check it. The unfortunate thing is that you've already kind of you can't do it retroactively.
I didn't mean that.
You kind of have to start over. Just kind of make sure you have that option.
But still good.
You want to do it right. Exactly.
The question, just confirming on the low difference that we need to change. So let's just say decrease.
Yeah, it should say decrease. Yeah, so I made a new version. I made a new version. And now it's supposed to be original. But then it changed it to 10,000. So it should be decreased from 10,000.
Did it earlier, like this morning, and I raised it to 90,000 because I thought it meant increase from like. I thought the typo was over here, but I didn't. It's good. Thank you.
Question. Okay, you don't have to do part E. So yeah, the part about refinement you don't have to do because we didn't go over refinement in the activity. Cool.
Yes.
Yep. Right. Any final questions before I close up? All right. See you guys Thursday.